Hey, welcome to the Explainer. Have you ever seen one of those massive container ships, a literal floating city of steel, and just thought to yourself, how on earth does that thing not just tip right over? Well, today we are going to dive into the incredible physics that keeps these absolute giants upright. All right, let's really get into this. I mean, you look at a 100,000-ton ship, a block of steel that's heavier than a skyscraper, and it just seems impossible. It just defies all logic that it can float so calmly, never mind stay upright when the seas get rough. So what's the secret? How does it actually work?
Okay, so to unravel this whole mystery, we got to go way back to the beginning. We need to look at a principle that was figured out more than 2,000 years ago. It's really the first clue, the fundamental force that stops anything from sinking.
And that force is called buoyancy. You've probably heard of it. It's Archimedes Principle, and it's actually beautiful in its simplicity. All it means is that the water an object is sitting in, it's literally pushing back. The more water that object displaces or, shoves out of the way, the stronger that upward push from the water becomes.
So what you're seeing here is basically a constant battle, a tug of war between two forces. You've got gravity, the object's weight, pulling it down, and then you have buoyancy pushing it up. It's pretty simple, right? If gravity is stronger, the object sinks. If buoyancy is stronger, it floats. And if they're perfectly matched, well, that's when you get what's called neutral buoyancy. Think of a submarine just hovering in the middle of the ocean.
Okay, so we've established that things float. Great. But just floating isn't the whole story, right? Floating is one thing, but being stable, not tipping over, that's a whole different puzzle. So to really get our heads around stability, let's start with a simpler case. Something that's totally underwater, like a submarine. Now, inside any object that's underwater, there are two really important, kind of invisible points we need to think about. First, you've got the center of gravity, which we'll call G. Just think of it as the single point where all the object's weight is concentrated. Then, you have the center of buoyancy, or B. That's the center point of the hole the object made in the water, and it's where that upward push of the water is focused.
So for something like a submarine, this is the magic setup. You want the center of buoyancy, B, to be above the center of gravity, G. Why? Because if the sub starts to tilt, these two forces create this beautiful, self-correcting action. It's like a pendulum. Gravity pulls down on G, buoyancy pushes up on B, and together, boom, they create a twist that pulls the sub right back to where it should be. It just naturally wants to be upright. But what happens if you flip that? What if the heavy center of gravity, G, is above the center of buoyancy, B? Well, now you've got a recipe for absolute disaster. Any tiny little tilt is going to create a pair of forces that, instead of correcting it, actually work to flip it over even further. It becomes totally unstable and just wants to capsize.
Right, so here's the most important thing to remember for a submerged object like a sub. Because it's completely surrounded by water, the shape of the water it displaces never changes when it tilts. That means its center of buoyancy, B, is totally fixed. It doesn't move around. And that makes the rule for stability super simple and absolute. Just keep B above G, period.
Okay, but here comes the plot twist. You see, that simple little rule we just learned, it kind of gets thrown out the window for a ship that's floating on the surface. In fact, for most big ships, their center of gravity is already above their center of buoyancy. And based on what we just saw, that should make them incredibly unstable, right? So, what in the world is going on here? This is the real heart of the mystery. It all comes down to one thing, the water surface. That single interaction changes absolutely everything.
Because here's the thing. When a floating ship tilts or rolls to one side, think about what happens. A big wedge-shaped piece of its hull on that side sinks into the water, and at the same time, a wedge on the other side lifts out of the water. So the whole underwater shape changes. And because that shape changes, the center of buoyancy, B, actually moves. It shifts sideways following that new shape. It is absolutely not a fixed point anymore.
So you can imagine, this moving center of buoyancy was a huge puzzle for early shipbuilders. How do you design for stability when one of your key reference points is always moving? Well, to solve this, naval architects came up with a really brilliant idea, a theoretical concept that is the real secret to a ship's stability. And it's called the metacenter, or M for short. Now, this is where it gets a little abstract, because M isn't a physical point like G or B. It's a theoretical point, an imaginary spot that literally pops into existence only when the ship begins to tilt. The best way to think of it is as a new, temporary pivot point for the entire system. And this shows you exactly how it works. So watch this. Step 1. the ship tilts. Step 2, the underwater shape changes, right? And that means the center of buoyancy shifts from its original spot, B, to a new spot, which we'll call B1. Now, imagine drawing a perfectly vertical line straight up from that new point, B1. The exact spot where that new line crosses the ship's original vertical center line, that is the metacenter, M. It's amazing. The ship's own tilt creates the very point that determines whether it will survive.
So, we have a new rule for ships on the surface. Forget B being above G. The new rule is this. As long as the metacenter, M, stays above the center of gravity, G, then the forces of buoyancy and gravity will team up to create what's called a righting moment. It's like a giant invisible lever that powerfully pushes the ship back upright. But, and this is the scary part, if a ship is designed badly or loaded the wrong way and it tilts so far that the metacenter, M, actually dips below the center of gravity, G, that same lever action completely reverses. Now it's an overturning moment, and it will actively, forcefully work to flip the whole ship over.
And that little distance you see right there, the space between G and M, that is everything. It's called the metacentric height, or just GM, and it is the ultimate report card for a ship's stability. If that distance is big, the ship is called stiff. It'll snap back upright really fast and aggressively. If the distance is small, it's tender, meaning it has a slower, more gentle roll. But if M goes below G, you get a negative GM, and that means you're on a dangerously unstable ship.
All right, so we've got all the pieces of the puzzle now. Let's put it all together and finally solve our original mystery, how this incredibly clever physics keeps these giants from tipping over out in the real world.
And here it is. Here's the solution. A giant ship stays upright not just because it floats, but because its wide hull is specifically engineered to do one thing: to make sure that when it rolls, the center of buoyancy moves sideways far enough to keep that magical point, the metacenter, M, safely above the center of gravity, G. It's not static, it's a brilliant, dynamic, constantly self-correcting system. And trust me, this is not just textbook theory. This stuff is what naval architects and engineers live and breathe every single day. Every decision they make. How high can you safely stack the containers? Because that raises G, the center of gravity. How will the ship behave going from dense salt water into less buoyant fresh water? It all comes back to one thing: maintaining a safe, positive metacentric height. And maybe the most critical thing of all is making sure that cargo is locked down, because if that cargo shifts in a storm, a perfectly stable ship can become unstable in an instant.
So that leaves us with one final, pretty important question. If we understand all this physics so well, why do modern ships still sometimes capsize? And I think that leaves us with a really sobering thought. The engineering is, without a doubt, brilliant, but it's all designed to work within certain limits. And when a ship is confronted by truly extreme forces, we're talking rogue waves, monster storms, or a critical human error like that shifting cargo we mentioned, that elegant, delicate balance between G, B, and M can just be violently overwhelmed. It's a powerful reminder, no matter how clever our designs get, in the end, the ocean always has the final say.